Now what happens when the force is not constant, or maybe when the displacement is not along a straight line? Because we said that work was the force dot product with delta S, right? But what if the force changes? If over this distance the force was this much, but sometime later the force is less, how would you calculate the work done by that force? Suppose that in a situation where something like that might happen would be put a wire and put a little ring on top of the wire, and you pull on that ring with a force F in some direction. Let's suppose that you do it with constant force, but what's happening here is that the displacement vector is changing following that curve, right? So how would you calculate the work done by that force? What you would do is calculus. You would break this whole length into little pieces, right? Little vectors ds, right? At each location, the force is going to make an angle with the ds vector. At each location, you will have a different angle, right? So you will calculate in that little section how much is the work done by that force. So you will do a little work in this section, that is amount of work done in that little section ds will be F dot ds. The force, you can assume that if ds is very short, the force remains constant over that tiny little distance, right? If it isn't, take the distance a little smaller until the force does remain constant in that interval. So then you will add all of these terms, right? In differential notation, the summation is written by an integral. So we have the work along that path is simply the summation of the work done in every little section of the path. Okay? And the work done in every section is this. So you will do between the initial location and the final location. So that would be how you deal with that. So this is the general way to calculate the work done by a force. Now the next thing that we need to figure out how to do is what happens when we deal with more than one force. I already kind of told you that. But the general derivation of what you do is here. I'm not going to go into the details of the right-hand side. But basically what you start saying is that the net force is equal to the mass times the acceleration. That's just Newton's second law. Now you're going to, if the object has several forces acting on it, F1, F2, F3, and so on, and it's moving along some path, say the blue line, what you want to do to calculate how much is the work done between some initial and some final location is, well, if you start with that equation, you integrate over the path, right? You look at the net force vector at all locations, look what's the angle, multiply by the little distance ds, add over the whole path. That's the left-hand side. On the right-hand side, you have to do the same thing, right? If you have an equal sign, if you do an operation on the left, you have to do the same operation on the right. So the operation that I'm performing on that equation is I'm integrating the vector with ds over the path. So the vector on the right-hand side is the acceleration. I'm doing a dot product between the acceleration and ds and adding that over the whole path. Again, the details, I'm not interested in you being able to do it. I just want you to understand where that equation is coming from. So the left-hand side is the work done by the net force. That's the definition of work, right? The right-hand side gives you 1/2 of the velocity squared minus 1/2 of the mass times the initial velocity squared. You can look at in the book for the derivation of that. It's not that complicated. It's just replacing the acceleration in terms of the derivative of the velocity with respect to time, and then you replace that with the derivative of the velocity with respect to position times the derivative of position with respect to time. You do a replacement there, and you can get that result. But the important thing is that starting from Newton's second law, you can show that the work done by the net force is equal to the change in the kinetic energy in general. It is the net work that results in a change in the kinetic energy. If only one force had been doing work, then the work done by that force will be the change in kinetic energy. But if you have more than one force doing work at the same time, you have to find the net work. So this thing is called the work kinetic energy theorem. So again, let me remind you that the net force is the sum of all the forces acting on the system, and that the net work is therefore going to be the work done by the force 1 plus the work done by force 2, etc. You have to add all of those works. So suppose that I've already done the integration for you, right? Suppose that I already did the integration of force 1, force 2, force 3 over the path, okay? And suppose that I got these results, that the work done by force 1 was minus 10 joules, the work done by force 2 was 20, force 3, 50, force 4, minus 20 joules, right? So then I could ask you that if the object starts with 10 joules of kinetic energy, right, at this point it was moving already and it had 10 joules of kinetic energy, I ask you to find what's the final kinetic energy, right? Given the fact that you already know what's the work done by all of the forces acting on the block. So you're going to do the net work, right, should be equal to the difference in kinetic energy, the final minus the initial, right? That's the work kinetic energy theorem tells you that the net work should be equal to the difference in kinetic energy. Okay? So the first thing will be to do the net work. So the net work is going to be just add everything that you have, right? That's the definition of net work. So minus 10 plus 20 plus 50 minus 20, you get 40. Net work, according to the theorem, is going to be equal to change in kinetic energy, K final minus K initial. So if I start with 10 joules of kinetic energy, my final kinetic energy should be 50, right? 10 plus 40. So let's look at some examples, and we're heading towards the discussion about conservative forces. So what's the work done by gravity? So in a simple situation where an object is falling under the effect of gravity, right, the force of gravity is this red vector that I'm drawing there. And let's say that that object is moving between some initial and some final location. Let's say that the initial is higher than the final. So I'm interested in finding the work done by gravity. I'm going to describe the position of that object by a vector s sub I and by a vector s sub f, initial and final locations. Okay? So what is my vector delta s? Remember that that's involved in calculating the work. So what's the displacement vector? So displacement vector always goes from your initial location to your final location, right? Is the difference between SF and SI. The easiest thing to do is, like I said, draw a line between your initial and your final situation. That's your delta S, displacement. So the work done by gravity will be, we have the equation, right? Definition. The force is constant, so I just do the dot product between the force and the displacement vector. That's all I have to do. What's the force? I need to write it in vector notation, because dot product is a vector equation. So it's mg, but I have to put a direction, right? So I would put, say, j hat, right? And a minus to indicate going down. Yeah? And the vector displacement, I'm just going to write it in terms of sf and si. I'm trying to transition now between the variables that I'm using in work, which is s, and the variable that we use for potential energy, which is h, for height. So that's what I'm going to do next. So I'm going to call those heights hi and hf. Okay, different from the vectors. I mean, related, obviously. So minus mg in the j hat direction, dot product hf in the j hat direction minus hi in the j hat direction. Just writing things in vectors. So now what do? I split that dot product, right? I do this product, this dot product with this, and this dot product with that. So the first term will be minus mg hf, and then j hat dot product j hat. That's just one. Then the second term is minus mg times minus hi. So that gives you a plus mg hi. And the dot product between j hat and j hat is just one. So I got that the work done by gravity, I'm going to pull out a minus sign to write it in a standard way, is minus, what is this? mghf and mghi, potential energy. So I got that the work done by gravity is equal to the negative of the change in potential energy. Negative of the change in potential energy. The work done by gravity, if you're going down, is positive, right? Because the force and the displacement are in the same direction. So gravity is increasing the energy of the kinetic energy of the system. So the work done by gravity on the way down is positive. So this number is going to be positive. How is that related to the negative of the change in potential energy? What happened to the potential energy when you move from I to F? It decreased. So delta UG is a negative number for this motion. That's a negative. With a negative, turns into a plus. Okay, so that is connected. The positive work done by gravity is connected to the fact that the gravitational potential energy decreased. Those two things are connected. That's what the minus sign is doing, right? Your potential energy decreased, and the minus sign tells you that the work done by gravity is positive. Now the delta K, the amount of the change in the kinetic energy as that block is falling down, should be equal to the work done by the net force, right? The net force is just gravity because gravity is the only force acting there. And we just calculated the work. So that change in kinetic energy is going to be the negative of the change in the potential energy. The change in the potential energy with a negative sign is what I have here, right? I'm just going to plug it in there, back in there. And let me put the final stuff, the stuff that has a final as a index on the left-hand side and the stuff that has initial on the right-hand side. So what do we get to? We get to a very familiar equation, which tells you that the kinetic energy plus the potential energy at this point should be equal to the kinetic energy plus the potential energy at that point, right? Which is what you already knew, and you would expect that to happen, okay? So there's 2 points of view going on here. One is to think of gravity as just a force that it does work, right? And this is the amount of work that it does, and that work changes the kinetic energy, okay? So you would say delta K equals minus delta UG, which is, you can say that that is equal to what? If you put that together, delta K plus delta UG is equal to 0. That's what you would get, right? Or another way to look at this situation is to say that gravity has a potential energy associated with it, and that if I include the potential energy in my calculations, my energy should be conserved, where the energy is the kinetic plus the potential, okay? So with this point of view, I'm looking at gravity as being some external force acting on the system, changing its kinetic energy. With this view, the one that we've been doing in the last week, is gravity has a potential associated with it, and the energy is conserved, includes the kinetic and the potential energy. Think about, I guess I already mentioned that, but when the object is going down, what is the sign of the work done by gravity? We just looked at that. It was, the work done by gravity was positive or negative when the object is going down? Positive. Gravity and displacement, same direction. Yeah? Now, I can also look at this equation and decide about the sign of the work done by gravity, right? Because in this situation, delta U is negative. You're going down, so your change in potential energy is negative. When you put a negative in front of a negative, you get a plus, right? The work done by gravity should be positive for that situation. What I just said is here. Since the change in the gravitational potential energy is negative, then the work done by gravity is positive. Or I look at the directions. Force of gravity going down, displacement going down, dot product between those two vectors, it should always be something positive if the two vectors are pointing in the same direction. But now what if I throw this object in the air? I start with some initial velocity. The object climbs up, and the point F is higher than the initial point. So what is the work done by gravity in that case? Is it positive, negative, 0? The answer is it should be negative, right? So you can look at it two different ways. One way will be to think about what happens to the change in the potential energy of the block as it goes up. The change in potential energy as an object goes up is positive. More potential energy at the end than at the beginning. So delta U is positive. And then you refer to this equation that tells you that if the change in potential energy is positive, your work should be negative, the work of the force, in this case gravity. So that tells you that the work done by gravity is negative. Or you can think of it from the definition of work. Notice that on your way up, gravity is pointing down, but your displacement is pointing up because you're going up. Okay? So your delta S is up and your force is down. When you take the dot product between two vectors that are opposite in direction, you should get a negative number, right? Because remember that the dot product has a cosine of the angle between them. So if the angle is 0, you get cosine of 0 is 1. But if the angle is 180, you get minus 1. So your dot product is going to be negative when the vectors are opposite. In fact, the dot product is going to be negative whenever the angle between the vectors is between 90 and 270. 90 and 270, you will get a negative value. So we just look at the work done by gravity in a specific situation where the object is falling down straight. What if the object is not falling straight down, but it's sliding down an incline, no friction, and it's going from some initial height to the bottom? So now your displacement vector in that situation is not straight down. Your displacement vector is diagonal. It has a delta x and it has a delta h. Okay, so I'm going to calculate the work done by that force, the force of gravity, by using the definition of how to calculate work of a force. I take the force as a vector, minus mg j hat, and I do the dot product with delta s as a vector. Delta s has two components, delta x in the I direction and delta h in the j direction. So when I take the dot product, this dot product that, I will get 0, right? When I take this dot product this, why do I get 0? Because there's a j hat dot product I hat. Those two vectors are perpendicular to each other. So the dot product gives you 0. So my final result there is that's what I just said. You get 0 for the first term. The second one is minus mg times delta h. Minus mg times delta h. J hat dot product j hat is 1. So one more time, notice that I get that the work done by gravity is minus mg delta h, which is the same as to say that the work done by gravity is the negative of the changing potential energy, which is exactly what I got before. What did I get before? Before I had this object falling straight down at distance delta h. Now I have the object, let's say that it's sliding down the incline at distance delta h. The work done in this second situation, even though you see that the delta s is longer, right? But because the work is done with the dot product, that delta s being longer didn't matter. The only component that actually changed, that contributed to the work, was the component of delta s that was vertical. The other component of delta s didn't matter. So I could have had this inclined plane, or I could have had a longer one that takes me from the same initial location to the ground, and the work would have been exactly the same. It would not have mattered. Now things get even more peculiar when you consider a different shape. Suppose that now the object is sliding down like that, no friction. And it's starting from delta h, and I wonder how much is the work done by gravity when the object slides down that path. How much is the work done by gravity? So you might think maybe you have to integrate something, right? It's a two-dimensional situation. Maybe you have to do a path integral or something fancy like that. Well, we have the answer in the previous cases. We have the answer for the work done by gravity if the object was sliding down straight segments, right? If the object was sliding down this incline, right? Then we said that the work done by gravity was mg times delta h1, let's say, or h1, this height. Then the work done by gravity in this segment was mg times h1. That was a minus. So I know the work done by gravity in each segment. So what I can do is add the work done by gravity in the first slide plus the work done by gravity in the second part of the path plus the work done by gravity in the third part of the path, and so forth and so on. and this is what you will get. Minus mg h1, where h1 is the height of the first slide, minus mg h2, the height of the second slide, and so forth and so on, as many slides as I have here. Okay? So what is the net or the final answer for the work done by gravity when I start up here and I end down here? Minus mg times delta h, the total height from which the object fell. So that is a very surprising result, that the work done by gravity would not, I didn't specify what shape was this, right? The work done by gravity going from here to here is independent of whether I go this way or if I go along a straight line. Okay? So following that path, you get a work done by gravity, certain number. Following that path, you get the same exact number for the work of gravity. Following that path, you get exactly the same number. So when the work done by a force, in this case gravity, is independent of the path that you follow, then you call that force, in this case gravity, you call it a conservative force. It's a conservative force, and the conservative part means that this force is going to conserve energy. Conservative forces conserve energy.